Here's a walkthrough of problem set 1 from constant acceleration motion. My advice to you on all of these is to begin with a verbal description of the situation. So here we have a ball rolling down a ramp, and the whole way down the ramp, it's going to speed up. We should be able to recognize that just from our experience in the world. But what direction is the ball headed? That you need to consult the picture for. I see that this ball's headed in the negative direction. I've got this information here of a couple of positions, and there's an implied position up here of 50 centimeters. So if we're going from 50 to 25 to 0 centimeters, that means we're headed in the reverse direction, right? Numbers are getting smaller. We're headed the negative direction. Okay, so we're headed in the negative direction. Our initial velocity is 0 because that was given to us. Our initial position is 50 centimeters. Here's how I would do the position graph. Start at a position of 50, and sometime later at a position of 0. How do you connect those dots? This object is speeding up. I need this graph to get steeper as time goes on. Get steeper. All right, so how do we do that? How do we make a position time graph that gets steeper as time goes on? Here's how I'm going to sketch it. Okay. Headed in the negative direction, getting steeper as time goes on. Now, how about the velocities? We are told that the initial velocity is 0. Go ahead and put a point on the graph for that. We know that the velocity is going to be negative, so this is going to head down into quadrant 4 on the graph, somewhere down here. And I need velocities that steadily get more negative. So sometime down here, I need a pretty big negative velocity. Now, how about acceleration? This one has thrown all sorts of people for a loop. Acceleration. I want you to always remember the definition of acceleration as the slope of a velocity time graph. With that in mind, that means the acceleration is constantly a negative number. How negative? I don't have enough information on that, so I'm just going to pick a negative number. Let's make a few notes on here so that way we can have them forever, and then I'll rejoin you on problem 2. And boom, there you go. Okay, so I've added some notes here to the 3 graphs in problem 1. Let's move on now to problem 2. All right, again, I want you to start with a verbal description. This graph is completing this set of graphs is going to require you to recognize there are 2 different motions that happen here. At this point where the graph breaks, right, something changes about the object's motion. And in fact, before you get too deep into this, I would recommend that at 25 centimeters, you put a little dashed line. Something's got to change about your graph at that point. All right, verbal description. First, the ball rolls up the ramp while slowing down and with a positive velocity. Second, the ball hits the 25 centimeter mark and rolls at a constant velocity across the flat surface. Now, I'll acknowledge there's more than one way that you can read this picture, and that my second portion of the motion, assuming the velocity is constant, I'm making some significant assumptions here, like that ball is rolling across a pretty smooth surface and hits the 25 centimeter mark with enough velocity to carry it the rest of the way, that we're not dealing with a lot of friction. I'm hoping to simplify things here, not complicate. In fact, now that I've said it, that's actually a pretty good physics mantra: simplify, don't complicate. All right, the ball is slowing down initially, then moves at a constant velocity, moving forward the whole way. Start at a position of 0, that's on the picture, eventually reach a position of 25, and then eventually after that, reach a position of 50. how to connect the dots now. Moving forward while slowing down. Curve something like that. So now I'm just hand sketching these curves, and it's an approximation. If we're collecting data, we can plot specific points and get it more accurate. But now I've got to get from this point up to 50. So it's going to have to go off screen. So you'll notice here that the graph becomes linear for that last segment. Previously, it was a curve. Now it's linear. You'll also note that at the 25 centimeter mark, right? So let's see, how's this going to look? Right about here at the 25 centimeter mark, I'm making a transition from this curve that's getting shallower to a line that maintains its slope. It's important that that transition be relatively smooth. Okay. All right, let's continue on. What's happening to the velocities? Well, remember earlier I'd suggested that you use that orange dash line to mark off the spot where something changes. I'm going to use now a vertical dashed line, that's not it, that also shows us where something happens about the motion of the ball at that point. All right. First, we're moving forward, positive velocity, and slowing down. So we need to go from a large velocity to a small velocity, and then we're going to roll at a constant velocity. There's one. There's two. That doesn't look that constant. Let's see if we can do better. That's better. And then finally, we need to look at acceleration. Remember from the last problem, how do we read acceleration off a velocity graph? We look at the slope. So initially, my velocity graph has a negative slope. So I need to have a negative acceleration. And then later, no slope. So there needs to be no acceleration. It would look something along these lines. So these are the three answers to question number 2. I think by now you've seen enough to get an idea of how these problems work. I'm going to stop the recording and simply make a full solution PDF available to you. Best of luck, and please feel free to reach out if you are unsure how to do any of them.